Welcome back. And let's go over ways to optimize the learning process. Okay, so earlier we built a two-layer neural network in Python. We implemented it in a deep learning library in TensorFlow. And we noticed that we still had to manage quite a few things, namely your choice of activation function, your choice of optimization function, your number of training epochs, what learning rate you chose, how many layers you could use, and how many neurons per layer. And there's quite a few more hyperparameters to tweak and optimize. Let's go over some really good practices in building neural network models. Because really, it's really easy to train them, but it's really bad to train good ones. So a couple of tips. We're just going to go over some best practices that we've compiled over working on these things. First is pre-process all your data to have zero mean unit variance. Why? This image kind of makes the case for if you take your optimization space and it has zero mean and unit variance, it's actually much easier for the optimization function to find a point of convergence that makes sense. So would you rather have this like spiky optimization path or this fairly smooth optimization path? Answer is pretty obvious. Images will always have unit variance between features because all of the features in an image are pixels and all pixels take a certain range of values. But you can still take images and improve data processing for images. Now, a couple of neat tricks are you want to subtract the mean image from all images. Second is you might also want to subtract the per channel mean along each channel, and you'll always have the RGB channels to work with. Why is this interesting and important? Well, okay, ultimately, you want to maintain the variance of your dataset while canceling out. You just want to maintain the uniqueness of your dataset. And that is why subtracting the mean image doesn't actually remove the kind of data that you need in order to build an image classifier. So the next thing is talking about train test validation split. Earlier, we were checking the accuracy of our baby deep learning classifier against the training dataset. For those of you who noticed that it was bad and have been screaming this whole time, yes, you're correct. It is very bad. Do not do that. For machine learning, you really want to break your dataset into training and test datasets. For deep learning specifically, it's very important to also have a validation dataset. I guess also in like generic machine learning. So how do you use these three data splits? Okay, so first you want to train on your training dataset. And then you want to tune your hyperparameters. So then you want to use the validation dataset to check your hyperparameters and keep optimizing your hyperparameters until the model you build is performing well on both the training and the validation datasets. Once that's true though, you still want to do like a genuine first look test, because this validation dataset is no longer a genuine test dataset since you have been tweaking your hyperparameters to get it to that point. So you want to have one last small test dataset in reserve to genuinely check how generalizable your model is. A lot of machine learning is inferring from the visible evidence, where the visible evidence we have is, in this case, accuracy over training epochs. So if you have a model where the training accuracy is improving over time quite nicely, and the accuracy against the validation dataset is not quite as good as the training dataset, which, as it should be, it shouldn't be quite as closely trained on validation versus training. If it's too close, you might have some room to mess with things a little bit more. If the validation accuracy is garbage versus training accuracy, then you might be encountering a case of too strong overfitting on your training dataset. And you definitely want to tune your hyperparameters so that this moves up. So how big do these datasets have to be? The Udacity Deep Learning course has an interesting segment by Vince Cerf, who says that a change in accuracy that touches 30 examples in total is usually trustworthy. Good enough for him, good enough for us. So in other words, if your validation set size is 30,000 items, then you'll sort of know that an accuracy change of 0.01% is valid. If your validation set size is 3,000, then an accuracy change of 0.1 is valid. That is pretty good rule of thumb. You definitely don't want to be boasting about an accuracy increase of 0.1% if you only have a validation set of 100 items and a total training data set size of 1,000 items. It's probably no bueno. When you are training, you also want to balance data across the classes. So we really encounter this problem a lot when we're doing what we call needle in a haystack problems. For example, fraud classification, where you're trying to identify fraud versus not fraud, but your cases of fraud are substantially smaller than your cases of not fraud. Same with cancer, no cancer, anything that's like needle, like finding you have like one case of needle and 500,000 cases of hay. For image classifiers and for classifiers in general, you really want to have a roughly balanced split of data across classes, and also within the train test validation splits, you also want them to be evenly balanced. You can't train a dog binary classifier on pictures of just cats. So for people who have questions about what to do in those needle and haystack problems, outlier detection methods tend to give you a little bit of a sense of that. We're going to go over in a few moments ways of expanding your data set, given that you only have 100 images, how to use that to seed 1,000 more. The next thing you'll want to do is to shuffle the data to get rid of any ordering. Ordering will accidentally wreck your model's validity. So the idea is that if the first, let's say, 500 transactions in your store came from like a busload of people, all of whom were super trustworthy, then the next busload of people came straight from, I don't know, a con artist training facility, then what you want to do is to shuffle the data of all the people who came in to get rid of that like artificial ordering. How do you know if it's roughly unordered? You want to check the feature distribution along the splits to see if they match, meaning do the distribution curves for each feature across the training data set, the test data set, and the validation data set, are they roughly the same? This isn't going to be a problem with image data, again, because image data, the distributions are non-human generated by nature. So, before jumping into hyperparameter optimization, there's the whole dark art here, you first actually want to see if your core architecture and logic makes sense. The best way to do that is to try to overfit your model on a tiny fragment of your training data. If you cannot get to an accuracy of 100% on a small sample without any hyperparameter optimization, something very bad is happening with your core logic or your core data set. This is definitely something where you can check to see if something's going on, but you won't be able to use this to solve core problems. Okay, now let's talk about using tracking indicators to infer what is going on with your model. So in both life and machine learning, you want to make good choices. And because you can't interpret what's going on in a deep learning model directly, we have to infer how good your hyperparameters are from observing the effects of tweaking the hyperparameters. It really is like messy. It really is. There is no analytical way to solve for a lot of these things, which is why deep learning and machine learning are so different from classic programmatic computer programming where you define a set of instructions. So let's start with the loss function. Intuitively, well, analytically, we know that we want the loss function to converge somewhere where the loss is as low as possible. The shape that the loss function takes, and so this is earlier we were showing you TensorBoard, which will generate you as training goes on, the loss score of the model at that moment. And this is a model which has been trained across 100 different epochs and has like a very jumpy but converging loss rate. So the shape the loss rate takes will give you a hint as to how good your choice of learning rate is. But this is really like black magic. If your loss starts out moving down but your loss goes up, your learning rate is too high, your optimization functions bouncing all over the place in that loss landscape. Moving down too slow, it might be too low and you can tweak it up. It really is like quite hard to say. So let's look closely at this very high learning rate problem and give you a sense of like why that's a problem. So if what we want to do is remember that the learning rate is the step, the size of the step down you take. If A is a good size, then it'll take small steps towards the convergence. If A is too large, what happens is you'll take a step down here, but instead of taking a smaller step that'll take you close to optimal point, the big step takes you all the way across that side. And then you start going off on this crazy suboptimal, non-converging, it might still converge, but a very suboptimal place where your loss goes up for your model. Not good. Again, you can also see here that if your learning rate is too small, it'll take many training epochs to get to the convergence point, which is a problem if you don't have access to a supercomputer. So the accuracy function is the other thing we can look at to intuit what's going on. We want better accuracy over time. Just makes intuitive sense. You want loss to go down over time, and you want accuracy to go up over time. You also want accuracy not to be too different between your training and validation sets. Kind of pop quiz for you. Would it ever happen that your validation accuracy is better than your training accuracy? Think about it for 2 seconds. Put me on pause. Ask a friend. Okay, now we're back. So the answer is no. Your validation accuracy really should not be better than your training accuracy. In fact, if it is better, run it again. Like, maybe it happened in a 1 in a million chance, but I'm willing to bet money that that does not happen. Why? Because this represents the accuracy based against the data set you're training on. So this is when you see all the answers. The validation data set includes data points that your model's never seen before, so it just makes sense that their accuracy is a little bit lower. Sorry about that. With overfitting, with very strong overfitting, we see here training accuracy is high, but validation accuracy is very low in comparison. So we can address this with 2 methods, regularization and dropout. We'll go over that in the next set of mini lectures. So we can address overfitting by collecting more data points. Much later, we're also going to go over how to generate more data in situations where you only have access to a limited data set. But again, this is part of like the black magic of building neural networks. If they're really close together, it seems like there might be room to build a bigger model with more parameters and more generalizability. What's the ideal distance between training and validation? That is really up to you, your PhD advisor, whatever kind of model you're trying to build. So loss functions don't always follow those very nice sets of patterns that tells you what's going on. Sometimes they do very strange things. Like, for example, in this case, your loss model starts out kind of flat, never goes anywhere, and then suddenly begins training. Think about where your loss model is. Why would this happen? Think about where the optimization function is first initialized. They usually initialize with randomized weights. So if the weight initialization is bad, if the location on the loss landscape it initializes at is kind of odd, it can be that your optimization function is stepping around, but never really finding an improvement until like some point after a couple of epochs where it finally starts learning. So the weight updates part, we haven't really talked about it, but that's actually a really interesting part of your machine learning model. Think about it. A trained machine learning model is actually a trained set of weights W on some kind of predefined model architecture. But you have to start it at somewhere, right? You can't just start all of it at 0, because what's 0 times anything? 0. You will never learn if you initialize your weights at 0. And it will, think back to our vanishing gradient descent problem. If the weights stop moving, then it means your model has stopped learning. So the change in weights over training epochs also gives you a strong indication of, is my model learning or not learning? Okay? Okay. So you want a ratio of weight updates to weight magnitudes of roughly 0.001. If you want to look at the rationale behind this, we've linked the notes from Stanford CS 224D where they go over it in much more detail. But this rule of thumb basically holds true. When the magnitude is much lower than that, it can indicate that you're in a situation with a vanishing gradient where your model hits convergence, meaning it's no longer training, but it's not actually at a point of optimal loss. So think back to that vanishing gradient descent problem. Each layer that happens, updates propagate through the layers. If the weight updates in the first layers aren't really moving, that indicates to you that your gradient has vanished. Here is a graph of the sum of the magnitude of gradients for hidden layer neurons for the first and second layer of two different types of deep neural networks. One's ReLU and the second sigmoid. So this is kind of showing that over time, over the number of epochs, the sum of magnitudes for the first layer of this ReLU is very much approaching 0, which is not good because it indicates that it's not really training. And that's something which is actually visible to you this is actually something which can be made visible to you on TensorBoard. So if you are worried about vanishing gradient problem, eyeballing the weights of the different layers is a very good way to assure yourself that to rule that out as a problem or to identify it as a problem. Okay, next topic in this grab bag of topics. Let's talk about hyperparameter optimization. So if you think back to our different hyperparameters, there are two that have been appearing over and over again in the code we've been writing where I've been telling you please ignore it. Now's the time to think about it. So one is the learning rate and the second is the strength of regularization. These can take any number of values. So if you brute force all the possible combinations of the two things, you'll be training tens of thousands of models in order to figure out which one performs the best. Not super great. Here's an interesting way of deciding which parameters to choose. So this method comes out of Bergstra et al. Pretty interesting. So what this is indicating to us is that this is some unimportant parameter that barely affects model improvement. And whether that's the learning rate or regularization strength is not important. And this is the second parameter where it is actually some values here will actually result in a huge increase in performance. If you search in a grid pattern, what happens is that you actually never find this point of most improved performance. The trick with a lot of these hyperparameter choices is that they're not distributed normally. They're not distributed. You can't count on a normal distribution. You can't count on any type of sensible distribution. It is really all over the map. So the best approach, or maybe not quite the best, but a really effective approach is instead of using a grid layout of for every iteration, add 0.01 to your learning rate, to actually add some randomness to it. So the code here would be, for every iteration, add some random value between 0.01 and 0.05. And that will generate for you a much messier search grid, but also these 9 tries here and these 9 tries here, this is actually the best performing parameter selection. So this is an easy optimization to build in if you're kind of getting stuck on your hyperparameter optimization. Even so, you will probably be testing out the same model architecture across many different hyperparameter choices. This is from Andrej Karpathy, his cross-validation command center. Each one of these is the same model that he's running with different hyperparameter choices. And this is what he has to eyeball as his command center as he trains. Kind of scary. But hey, if one of the best AI engineers in the world does it this way, don't feel too bad about your own overloaded machine.